everyone. So, this is it. I'm just going to play with the robot for 20 minutes. Yeah. So, my name is Omar. I was asked to come down here and talk about either autonomous vehicles, ROS, anything involving that. I'm going to touch on a few different topics. I'm just going to kind of scatter cover a bunch of different things, and I'm sure you guys will have questions. And I'd like to think that I'm intelligent enough to answer whatever the variety of questions may be. But I suppose it'd be worth going over who am I. So originally, you had just seen a presentation on FIRST Robotics. Originally, I was a student on a robotics team, specifically the Thunder Chickens. Two-time world champion. Anyway, I was a student on the team for a couple of years, and I mentored 08, 09, 10, I think 5 years. And I can empathize with a lot of the material that was just covered in terms of the positive effect that FIRST teams have on students, communities, getting your feet wet with technology, obviously. After being on the Thunder Chickens, or actually during, I actually worked at Intrepid for a total period of, I think, 10 years. I learned a lot here as well, obviously, before starting my own company, which is CTR Electronics. The reason why that's relevant is because in the world of FIRST, the vast majority of electronics on the robot are from my company and have analogous functions in an automotive vehicle. We'll go over that in a minute. But my principal responsibility is software. Actually, let me do that. That's better. So who we are. At Cross the Road, we love making robot things. That includes robot controllers, motor controllers, things that activate your pneumatic solenoids, compressor, power distribution, and the only thing we love more than that is we love CAN bus. Now, obviously I'm a little biased, coming from a CAN tool company, but in my time here, it was pretty obvious to me that CAN, or networking in general, has a pretty major component, a major role to play in advanced robotics, or as well in the end goal of autonomous vehicles. But you can see up here, a lot of these devices are actually, every single one of those devices is a CAN device, a CAN node. And they all participate on 1 megabaud bus on FRC robots. And behave in a way that's somewhat analogous to ROS, which we'll talk about in a moment. But basically the goal is to set up a system like a car where you have multiple ECUs, and those ECUs implement individual features that each corresponding ECU is good at. So you might have one box that's very good at performing the radio wireless communication. You might have one box that's very good at updating the pneumatic actuators and making sure you have sufficient pressure in your system. Motor controllers, path plotting, camera decoding. I mean, the list goes on and on and on and on, which is why we make a lot of stuff. Just a quick note, I may reference some software things. We have a public GitHub that's available and has a lot of things on there. A lot of it's support for our products, but there's also a few genericized examples, like that robot, for example, the implementation of which is available online. So if you want to learn about PID balancing, gain scheduling, basic arbitrary feedforward, that would be a good platform to learn on. Quick note, ROS is a popular solution to the problem that I'm about to discuss. But if you find yourself overwhelmed, you find yourself, wow, this is too much, there are alternative frameworks out there if you just want to get a robot up and moving, you want to learn basic telemetry control, teleoperated control, learn how to debug simple software. So if you're super new to, I have a thing with wheels, I want to learn how to get it moving, there are cheap alternatives out there, including our control system, which is C# based, or Arduino, or Raspberry Pi, etc., etc., etc. And obviously FIRST. Oh, quick shout out to the FRC control system. This is the electronics that you find on the robots that were covered in the previous seminar. So, I mean, it's wired by high school students. And, I mean, this diagram is analogous to a wiring diagram in a car or an advanced consumer appliance. So, all I really want you to take away from here is that on a complex system that does important things, you have a lot of a lot of electronics that have to communicate over a network. Let's see. That show up? So in the world of FIRST, the interoperability of all of the components communicating together is done via the robot control system. But coming out of academia and open source community, there was a new method for allowing actuators and digital controllers and path plotters to communicate. And that thing is called ROS, or Robot Operating System. Although ROS stands for Robot Operating System, it's really more of a framework. It's the rules and means by which every ECU or computer in your platform communicates with each other in a standard way, so that you don't waste a bunch of time writing a bunch of stuff from scratch every time you want to build a new robot. If there's anyone here involved with FRC, you can kind of empathize with that, where every year you don't necessarily start from scratch, but APIs change, the devices may change. The first couple weeks is spent sort of re-architecturing and rewriting the low-level platform, the low-level software platform of your vehicle. ROS is somewhat of a solution to that in that it provides a common framework for things to communicate with each other. In the world of FRC, there was actually a team that attempted to deploy ROS on a robot, and they are called the Zebracorns. They're a team we sponsor, and a lot of what I'll be citing is pulled from their white paper. So if you ever want to get into the nitty-gritty, I strongly recommend going over to their website and downloading their ROS paper. Even if you're not involved with FRC, because it goes over installing individual components, and I won't necessarily get into that, because there's a lot of detail there, and you really want to take your time with it. So where is ROS used? I mentioned that it has a component in academia. Professors love it. It saves them a lot of time in developing curriculums because you can have a commonized software tech that you can bring your students into, install, learn, and then employ the algorithms, strategies, closed-looping methods, spliners, etc. that they learn in class. And they can also find examples that are already implemented for them, which is really the strongest thing about ROS is the proliferation of libraries. And I think, just going onto the ROS website, you can find a ton of libraries. ROS has a very permissive licensing model. So if you're a company that wants to support your peripheral, your product, with a closed source or proprietary driver, you're free to do so. If you want to put together an open source driver showing how to do extended counting filter on a IMU solution, you could throw that out there. It's very, it's low barrier to entry to get your stuff posted and tested on ROS. And as a result, there's a wide proliferation of, I mean, just looking at the list, on here is Cartographer, which is a ROS node that will actually do the math to figure out how to plat your robot through a course. There's a bunch of SLAM implementations, which is all of it's localization, or also called sensor fusion, where you have a bunch of sensors that tell you where you are in the world, but you have to crunch the math to fuse it all together. Some of your sensors may be redundant. A lot of this stuff is very complex. And to be able to go online and just pull an example down and see it work is very powerful. There's also some degree of interoperability, depending on which drivers you use, but the advantages of which range, depending on whether you're using a common hardware platform or not. Another big advantage is telemetry. So telemetry means, it's synonymous with instrumentation, which means I want to see the output of all my sensors. I'm driving my robot around, life's good, and then all of a sudden it does something weird. I should have gone straight, but it didn't go straight. How nice would it be to be able to plug in a device and get all of the sensor outputs of your platform similar to an instrumentation panel cluster in your car? In ROS, every message between each node is set up in a way where you can very trivially plug in and plot, capture, display an RViz. It's very similar to what Vehicle Spy provides at the CAN bus level, but it's just one more level abstracted where it doesn't necessarily have to be CAN. It's just the ROS network, and the software modules that I had up earlier auto-register standard messages, and then you get to tap into them very quickly, which is better than like writing your own telemetry from scratch, which you often have to do in the world of hobbyist robotics. Lots of libraries exist, mentioned that. Some of these things I didn't mention, camera processing, AI, obstacle avoidance. There's a lot of good stuff there. So if you're going to start dipping into ROS, as we found ourselves doing recently, because a lot of our customers have been asking us for it, we started with ROS Kinetic, which is every version of ROS starts with there's a K version, the next one was KLMNO. I'm not sure what version they're up to now, but at the time, ROS Kinetic was the stable version. So that's what I'm going to recommend for now, if you find yourself wanting to install ROS and start playing with it. Is there anything else here that's relevant? It's good to know that the Open Source Robotics Foundation sort of sponsors and runs the ROS distributables, so they're the ones who primarily do the hosting. I'm not sure what this is. Must not be important. So to get started, I recommend the following 3 steps, or 4 steps. First off, if you don't know Linux, learn Linux. I was a total Linux noob. So I had to learn Linux before I even started manipulating, installing, testing ROS. So what that means is, and this is a reason why Raspberry Pi is useful, learning how to set up SSH, learning how to just navigate the shell, learning shell script, basic shell script, because you're going to find yourself getting sick of running the same ROS commands over and over again, and then just running it once into an SH file. At the time, ROS Kinetic was recommended with Ubuntu 16.04. I don't believe that's changed, but I claim if you use 16.04 Ubuntu, you'll be fine. You won't run into any major hurdles. And in the context of Raspberry Pi, I would recommend Ubuntu Mate, which is basically the RMHF compile attempt at Ubuntu 16.4 with some stuff ripped out. So if you're already familiar with Linux, you kind of know the treacherous sea that is build systems. Because for as many programming languages that are out there, there are even more build systems. At least it seems to be that's my one critique of developing software on Linux. Luckily, with ROS, they baked in a pretty reasonable, pretty easy to use build system called Catkin. So one of the next things you'll be doing after you git clone the ROS packages will be learning how to use Catkin to build the modules. And again, I'm a noob at this stuff, and I was able to get it to build, which is a pretty good indication that you'll be successful. After you're able to build, the third step will be learning all of the commands. Luckily, all of the shell commands start with ROS something. So if you want to peek on all of the topics that are running, you type in ROS topic. If you want to launch something or restart a service, it's ROS launch, and then the name of the module. So it's pretty consistent, and I find navigating documentation on the ROS website to be pretty good. And then finally, if you're interested in CAN bus, which I obviously am because we sell CAN peripherals, it would be worth learning Socket CAN. Socket CAN is the Linux standard means of supporting CAN gateway or CAN tool device, including and not limited to Intrepid's product line, including Value CAN. That's what we use at CTR. There's a bunch of hobby stuff out there, Cannibal, Candlelight software. We even recently updated or released the software ports to the Hero control system. That's the robot dev board that we sell so that it shows up as a socket CAN device. So if you care about CAN bus, if you have motor controllers from the world of FRC that are CAN bus and you want to leverage the advanced features of the Talon, Victor, etc., socket CAN would be the way to go. And that's true even in non-ROS platforms. That's what I would recommend. And just some quick screenshots of available CAN solutions. I made the value CAN center and bit, right? Yeah, okay. So, some boring stuff. Learning the terms is important. I constantly mess these up because I'm dumb. But good thing we have documentation for me to reference when I go back and haven't done ROS in a while. I need to go back to it and get something working. ROS centers around nodes, topics, and messages. Nodes are this is pulled from the Zebra Core documentation. A node is a single process which performs some sort of computation. So think of like a software controller, a device who's a piece of software that produces something.Maybe it's a target heading for your obstacle avoidance, or target velocity in order to achieve some results. Maybe you have a camera processing node that gives you the centroid of the target, X and a Y, a thing to follow or a thing to avoid. By organizing the logic of your robot into nodes, that allows you to start to identify the signals that you need to pass between them. And those signals are stored in ROS messages. ROS messages have predefined data types, passed via network between nodes. So if, let's say, your camera node produces the target, does all the math, does the canary operator, and looks for a target, has a color pattern to look for, it will then produce a, say, two-dimensional target via a standard message. And then in the software API, you create that message, and then at that point, the node is done. That node is a separate piece of software that's maintained separately. Knowing what that message is allows you, or your technician, or someone on the product line, or another student, to go in and tap in with a visual interface like RViz, pick up the message, and plot it, debug it, tell the software engineer that they screwed something up, etc., etc. I often confuse ROS topics with nodes, but essentially, a topic is identifying the entire, so in Illustrated is a teleop turtle and a teleop sim. Turtle is a node. Turtle produces a command velocity. Command velocity is a signal that's embedded in the message, which is instrumentable. That goes into another node called turtle sim. But the entire topic, so that covers the entire, you can reference the entire relationship as a topic. And that's relevant because when you're in shell, you may want to be able to enlist all of your relationships, the point-to-point relationships, and restart something, shut something down, or replace it with a different implementation. It's another way to organize the functionality of your robot. And it works well in that there are tools that will scan your nodes live and then produce documentation with arrows and diagrams to show you how your robot works. If the robot's simple, you don't really need it. But in the context of, say, driving a vehicle, there's a lot going on there because you've got a ton of sensors. The sensors have to be processed. The sensors have to be fused. They have to be localized so the car knows where it is relative to other things. The car has to look for obstacles, react, make decisions based on them, and then it has to path plot, knowing what the limitations are of the physics of the car. Because the software can't just say, okay, I'm traveling, stop. Physics says, no, you can't do that. So there's a physics model somewhere. All that stuff runs concurrently, and organizing as ROS topics is a way to accomplish that. It's also worth noting that ROS nodes can publish data, and they can subscribe to data. So publishing is simple. This is the message that this node produces. Back to my camera node, it publishes the centroid target. But what the rest of the system does with that target, maybe it follows it, maybe it deviates away from it so you don't hit something. That's dependent on other nodes that subscribe to that signal, to that message. And although it's a simple concept, it's powerful in that any given node can subscribe to whatever variety of messages, including, hey, I want to write a node that just collects everything and then data logs it, or plots it, or does some kind of sanity check. Let me make sure these three signals have an average value that's within each other. I can just, without too much prior knowledge, create a new node, subscribe to those signals, and then write software that does that. Or better yet, I can delegate that to another person who may not understand how the rest of the system works, may not understand if there's a camera, if there's a gyro, if there's an IMU, what the number of motors are, if it's a combustion engine. As long as they have documentation that tells them this message will give you this information, it allows you to chop up your functionality in a way where you can make each piece so simple that it has to be bug-free, as opposed to making something so complex that it's never bug-free. I mentioned that we make CAN devices. We've been supporting the FRC community by providing software libraries for our CAN peripherals, our Talon motor controller, our Pigeon IMU, etc. What we've been doing recently, which is part of the reason why we had to learn about ROS, other than our customers kept asking for it, is that we wanted to take our libraries, which are targeted for a control system that's Linux-based. So we've been supporting a multi-build strategy where we now recompile our libraries for Ubuntu Linux or Linux Desktop, Raspberry Pi, which is Linux Linux HF, Linux ARM64 for the expensive hardware, and that allows our customers to be able to buy a Raspberry Pi and get a CAN solution, their favorite CAN solution, hook up the same robots that you would build in FRC or similar, and actually navigate them, bringing down the advanced ROS, path plotting, EKG, all the good stuff. But in order to do that, we had to demonstrate how to make this stuff work in ROS. So it behooves me to mention that on one of our GitHub repos, we actually have an ROS port with our libraries built in. This has been tested on Raspberry Pi, where we demonstrated driving a robot around. So we had a ROS node for joystick, ROS node for the motor controller, ROS node for a differential drivetrain, which means you've got a motor on the left and a motor on the right, kind of like this, but 4 wheels instead of 2. And what do I name this? Oh, and then a LiDAR. And the LiDAR we would just dump to a plot and then just show people how it works. This is the exact source that we use to get that working, and the CAN solution for that was a Cannibal, because we were learning about the different CAN solutions out on the market. So it's up there if anyone wants to look at it. I should probably show some code. To be fully honest, I wrote very little of this. I actually had my intern do most of the work. But this source code is very similar to the source written, implemented, tested by the Zebracorns. So I again recommend going to their website if you want very specific details on how to get going in the context of FIRST. But the major takeaways I just wanted to show here was the Talon up top that's our library. That's just standard C++. It's the class. And below, do I get a mouse? I guess I don't get a mouse. Basically, there are these member variables that get updated by you. And in software, you define this concept of a joint, which is yet another ROS term, which is somewhat analogous to what we covered, but not quite. A joint is a point-to-point connection with messages, and you just basically update those signals if you're a publisher, and if you're a subscriber. A framework creates basically a function for you, or you type it out following their template, where you're able to pull the data out, process, and then update whatever it is you need to update. Depending on how you set it up, you may create a MSG file. It didn't fit in one page, so I chopped it and put the other piece there. But you can see in the list is a all of the things that I would want in the context of a motor controller. So with our motor controller, with our talent, we have its mode, the demand, which is how much throttle to give it, basically. Target position, how much voltage it's applying, current it's applying, its temperature, whether there's a sensor, what kind of math the sensor uses. So this isn't necessarily the best approach, but there's a method to strip out all of the signals involved with whatever nodes you're developing, or you can do it programmatically. And my understanding is it's almost always done programmatically. When we got started, there's kind of a cart before the horse thing where we want to build a robot with ROS, but we don't know how to build a robot with ROS, so we need a robot with ROS to learn how to build a robot with ROS. The last time we did research, there were a few platforms that were in our price range. What we ended up settling on was the TurtleBot, specifically the TurtleBot Burger, which is to the far left. I liked it because it was Raspberry Pi based and it came with a LiDAR. But then when we studied it, it appeared to me to be the kind of the cheapo Chinese knockoff LiDAR. It's not an RP LiDAR or anything like that. But it still worked well for the academic purpose of learning how to get this working. I should mention that you could also do a great deal of this in simulation. Gazebo is well supported in ROS. So if you don't want to buy hardware at all and just want to make a virtual robot that virtually spins on your monitor in simulation, that's totally possible. But we wanted a physical platform because our ultimate goal was to produce a robot that uses CAN bus, not PWM servos, not anything small and rinky-dink. These are simple PWM. They don't travel very fast. What we ended up doing was ripping the wheels, the servo out, and hard strapping it to our chassis. And I'm not sure if you can see, you might be able to see laser pen. Let's see if this works. So right there is a cannibal. And that has a USB connection to the Raspberry Pi. This is the LiDAR. And all the good stuff is behind the TurtleBot, unfortunately, which is all the FRC equipment that we manufacture and sell. And for some reason, the balance bot, same balance bot that's over there. Now, one thing I really wanted to show you, let's see if I can figure this out. Do this. Does that render? No, not quite. Oh, wait a minute. Almost got it. Well, I'll tell you what. I wanted to demonstrate to you kind of the reasons why this is useful. Now, what I'm about to show you is kind of cheating. I'll explain why that is in a moment. Let's connect to the internet. When I saw this was kind of the thing that made me want to buy it. Slam YouTube. Anyone who's ever done any kind of robotics can appreciate the difficulty of what's going on here. So what we have here is a TurtleBot that's driving around, and it's somehow learning the course, the rooms, the hallway, the topology. It's localizing where it is, and it's doing this real time. So, how many, I think this question was asked, is there anyone here who's familiar with FRC, been on an FRC team? Know what that's about? Okay, a few. No, maybe two. This is on a level of difficulty. This is the next level, I would say, of technical challenge. Because there's several things going on here. If you were to do this from scratch, first, you would have to make a robot that can navigate or understand how it's traversing. And normally you do that with encoders. You have a sensor here, you're counting wheel rotations, you know the diameter of the wheel. So you can pretty much figure out if you've traveled 10 feet, if you've turned, but there's an error there. So what we can do is we can throw in an IMU or a gyroscope. We got to calibrate the gyroscope, so that's going to have some error. But we can do some localization. We could throw a camera on. The camera could look around and do math, and then figure out where it is relative to an obstacle. But at some point, the robot's going to move. Well, if the robot's got to move, it needs to track its relative distance to local obstacles. It needs to do this in real time to be useful or to be cool, like this demo. And if you want to remember the topology, remember that there was a hallway back there where the bathroom was, where the last obstacle, blah, blah, blah. You have to store that in memory in a way that's useful so that you can retrieve it later. Over on the right is RViz, an example ROS node that subscribes to all the signals. And then with the right visualizations, you can do something useful and impressive. And, figure out why your smart Roomba should have stopped at the leg of the staircase instead of falling off, or whatever robotic problem you're trying to diagnose. Let me get back into this. Oh, PowerPoint crashed. That never happens. Okay, and yeah, that works. Cool. So where were we? All that for a YouTube video, but I think it was worth it. So that's a lot of good stuff. What are the cons? Why aren't we using ROS for all the things? ROS has some limitations. For one thing, security is a limitation, though that may be improved with ROS 2.0, which the open source community is currently developing. There may also be some alternative solutions that I'm not fully aware of as far as implementing security in ROS. I mean, of course, you can always implement your own encryption inside of whatever signals you choose to bounce between your nodes, but then, it sort of hurts the whole point of it, where, well, now you can't get into your telemetry. So maybe you design it in a way where you turn the security on or off. And it's a hard challenge to solve without compromising all the other things about ROS that are beneficial. But it's slated for the to-do list for the ROS 2.0, roadmap. Driver development can also be kind of a nightmare because you have to learn all the things that an ROS node has to do, and it's not a trivial amount of software in terms of lines of code. But there are a lot of examples out there. So if you've got Linux down, if you have everything installed, if you're comfortable with Catkin build system, and you went over the examples and you kind of get it, then you're probably a good candidate to just write drivers from scratch. But not everyone has that level of expertise, at least not when they start. So driver development can be frustrating, especially if you're using a piece of hardware that already isn't supported by the community. Keep that in mind if you're going to design a robot hardware first, thinking that you're going to use ROS. The other compromise is processing power and cost. So the video that I showed you was sped up. That's what I meant when I said that they were kind of cheating. From my sources tell me that, for the most part, ROS is useful up to, when you get to about 3 feet per second in translational speed, which is pretty close to what this guy can do. Maybe a little bit faster than that. 1, 2, 3, a little bit faster than that. So once you start getting a little bit faster than that robot, the processing tasks tend to hurt you unless you run on a really beefy piece of hardware. So for Raspberry Pi, if you're doing something that's not trivial, you're going to run on a CPU. I think even in our demo where we were just driving the robot and broadcasting the point cloud from the LiDAR, I think we were near 50-60% on our Raspberry Pi. Now there's solutions to that if you're willing to spend. The Mac Daddy hardware right now for this kind of thing is the NVIDIA Jetson TX2. It sells for 500 or 450, if I remember right. I'm always confused about that number, because I never remember what it comes with.
$300 for students.
It's 300 for students.
That's about development kits, so with the more.
So my understanding is that that's also true for FRC teams. And that number is magic because that is the maximum number, that is the maximum amount a team can spend per component. Which is cool. Yeah, without platform specific, we run about 50 per second. Okay, so yeah. There's possibly a cheaper solution. I did very little research on this. But someone pointed out to me that there is an ROS serial module that has been ported to Arduino. I think there's an XP port out there, and maybe a few other peripherals. I don't know much about it, but it's worth looking into. My understanding is instead of using a traditional LAN, they use serial somehow. So I suspect they're compromising on bandwidth, and CPU because it's an Arduino. But if you're interested in a low effort, low force way to get into ROS, this might be a better solution. I just don't have a lot of information on it, but I felt it'd be remiss to not mention it because we'll probably be buying a few Arduinos. We'll do our research on it as well. Anything that's very cheap is interesting to me because cost tends to be the ultimate barrier for ROS, but I think that's getting better as more platforms are being supported. Yeah, and that's it. Thank you. If you guys have questions, I'll do my best to answer.